And okay, this talk it's just an introduction to what it's the research that we are doing, a part of the research that we are doing in our group. I just put the time so that yes, so that I don't go too much outside time. The point is that, and here it's a question that I put in this at the beginning of this talk. It's just what is the best ligand that can fit a nanocrystal, and this is something that we would like to do through this new trendy approach that is machine learning. So it's part. It's a way that we can use in order to find the best ligands that can fit the surface of a colloidal nanocrystal, whatever nanocrystal we have. And at the moment is like that we have to think a bit, because when you use this new technology like machine learning, you have to collect lots of data. And then you have to you have to be also intelligent enough, like not artificial, but intelligent enough to understand what are the features that you want that these ligands have in order to fit the surface of a nanocrystal. And the feature can be, for example, bulkiness or some the binding group to the nanocrystal. So the solubility of the nanocrystal in the solvent where you do the synthesis. So the point is that when you face this, then it's already becoming more, let's say, challenging how the way that you just define the best ligand to fit a nanocrystal. So, and the point is that also that these properties, the properties that you are interested of the ligand to fit a nanocrystal surface, will come also by analyzing the thermodynamic of these ligands on the surface of nanocrystals. And for this reason, we had to put down a framework for this binding of ligands to the nanocrystal surface. And you can find on this paper a work that I've done together with my PhD student Juliet, in which we study the thermodynamics. This fit also well with the previous talk from Jonathan, that made actually a nice introduction for this talk, because they're they're quite connected. But why we have to do this? I mean, if you think about it, and I mean, if you're a bit in the field, I mean, especially students, new students, or someone that just entered in the field, especially from the synthesis point of view, you immediately realize that in order to synthesize these nanocrystals, you mostly use the same type of precursors, basically. So what you change probably the metal, because you want to do a different type of inorganic core, so an inorganic nanocrystal. So if you want to do you want to change the metal in the core, then you have to use a different precursor. But then the precursor that you use, the organic part of the precursor, with some exceptions, are always more or less the same. And here I just make an example that we have only basically mostly oleic acid or oleilamine. But are these the best ligands that we can actually use? And this is the big question. I mean, are there any better ligands that we can actually use? Especially considering that if you just screen available databases of structures like PubChem, I'm not going to Sigma Aldrich because that includes the purchasable products. But if you look in PubChem it's a little bit more extended type of databases, because it includes also purchasable product, but also some ligands, some organic molecules that have been synthesized that you can find in the literature. So in the literature, you can still find something that it's probably not purchasable or that you can synthesize in situ. But how many structures there are in the PubChem database? And the number of structure that you actually have, it's quite large. It's 110 millions of compounds. I have to say here that of total organic molecules that in general have been synthesized or are actually purchasable or accessible, let's say. I have to say here that at the beginning we started to analyze some other databases that are available, but these databases are based on some sort of artificial intelligence approach on how to combine organic atoms like carbon, nitrogen, and oxygen together, satisfying some chemical rules, and then they use some statistics in order to combine them and create a new molecule. And we immediately noticed that these databases would grow very large. So especially there are databases that can be as big as billions, 200 billions of structure only by, for example, considering atoms, molecules up to with an organic chain up to 15, 16 atoms. But then we started with this, but then it became very clear that it was not manageable because, and also we noticed that many of these structure, like already from a chemist intuitive point of view were not very good. So then we decided, okay, well, let's switch back to the PubChem database. And then we started to sort this PubChem database in order to find, for example, with one simple rule that was our first rule, that is we assumed that the ligands that you want to bind or you use as a precursor in your synthesis, it's made only by one anchoring group. And the one anchoring group can be a carboxylate or like Jonathan before said, a phosphonate, a sulfonate for especially for the anion type of ligands. Then we included all type of ammonium that could replace the cations at the surface. Or we add also Zwitter ions. Maxim is the expert of Zwitter ions, and where you actually have the two binding groups. And then we said, okay, how many just by using this simple rule you can actually form? So how many of these you can actually sort from this database? And then you actually can see that about 70% of the structures that are in the database already disappears. And if you just want to include anions, you see that the carboxylate are dominant, and there are about 10% of the database. I mean, 10%, it's a couple of millions of structure, 1 million of structure. But we noticed that, okay, these are already manageable amount of ligands that you can actually do. So I stop here on this part. So this is just to show briefly what we are doing in our lab. This is a work that is been done by Francesco Zaccaria, that is a postdoc in our group. And the main point is that now we are computing intrinsic features of ligands that we can actually use to sort even more ligands. And one of these is also the bulkiness. So we have to be very careful with the bulkiness of ligand. One important thing, this is just the last thing I would say on this topic, is that ligands have to be, these properties have to be calculated very fast. And even if we want to use a DFT, like computational methods like DFT, they might be, also DFT might be too slow to collect lots of data for these ligands. So we have to find new strategies that we are testing now in our lab in order to compute these properties. So I don't want to spoil too much here. It's just something that we are doing. And the point of this talk, it's just actually that we have to do understand which properties we have to compute. In order to do this, we studied better the chemistry of the ligand binding to the surface of colloidal nanocrystal. So, and here we immediately faced what was proposed by Peng. Peng proposed the idea of entropic ligands. So you can imagine that these nanocrystals can be soluble in the organic solvent where you have prepared them. So you can actually see the ligand. And then there is an equilibrium between dissolution, precipitation of the ligands, where they aggregate and precipitate, and the dissolution equilibrium. And there is an aggregation term, so where the ligands branch, interact with each other to most likely to the alkylic chain of the ligands, and this shifts the equilibrium towards the precipitation. And then there is another contribution that is an entropic contribution that tends to shift the ligands in solution, the nanocrystal in solution, because the ligands want to be free to move, and this is a term that shifts the equilibrium toward the nanocrystal in solution. This because when they branch, these degrees of freedom are blocked, and so you have a big loss of entropy change. And this gave an idea to Peng that to modulate the ligands that you have on the binding to the nanocrystal in such a way that you can branch them, like you actually do here. So you have this branched ligand that at some point they branch. They can branch at the beginning or in the middle of the alkylic chain. And what happens is that by branching, you prevent aggregation. So you prevent the term of aggregation becomes smaller, but at the same time, you increase also the number of degrees of freedom on how the ligands can move on the surface of the nanocrystal. And this shifts a lot the equilibrium towards the nanocrystal in solution. And this way, you can prevent aggregation on nanocrystals, and then you increase the solubility of the nanocrystal in the media, where you do the synthesis. And this Peng showed that this is a way that you can proceed to improve the quality of your sample. There is a point here that was not actually included in this thermodynamic picture, is the fact that when you increase the entropy of the ligands when they are on the surface, so if you branch the ligands, as you increase the entropy of the ligands at the surface, what happens is that in reality you have another equilibrium that is the binding of the ligands to the nanocrystal. And so what could happen is that the branching of the ligand could also induce a displacement of the ligands from the surface of the nanocrystal, because now the ligand is branched, has many more degrees of freedom, and then if you move the ligands in solution alone, so displaced from the surface, it has also a big effect, an entropic effect that increases the entropy when the ligands move detached from the surface of the nanocrystal. And this is something that probably you want to prevent, because you don't want the ligands to detach from the surface, because what happens is that if you have a surface coverage, a ligand coverage on the surface that is low, this probably is linked to the fact that you have increased the amount of defects on the surface of the nanocrystal, and then you can introduce trap states. So, so the point is that if you combine these two picture together, so the dissolution of the nanocrystal, precipitation of the nanocrystal that is on this side, together with binding and displacement of ligands to the nanocrystal of the surface, what you want to do is the following. You want to shift this equilibrium that is on the left towards the surface, so you want to shift this equilibrium towards the nanocrystal passivated with ligands, but you also want to prevent the precipitation of the aggregate. And then you have to design the ligand in such a way to satisfy these characteristics. So what we have done is, maybe I don't want to waste too much time, because otherwise I don't have the time to tell everything. So you want to have this high passivation that I was telling you before. So you want to improve the binding of the ligand to the nanocrystal, but at the same time you want to avoid the precipitation. You want to have the nanocrystal still soluble. So you want to prevent aggregation. So this part, the second part, it's the part that was demonstrated by Peng and that I gave a brief introduction. So that I will not address it explicitly. I will address mostly in this talk this first part. Another thing that I have to put into account is that we can decompose, and this decomposition of the binding, the binding energy, or the free energy of binding. Here we do some approximation. We consider also standard condition. We don't consider concentration of ligands. We consider infinite dilution. So the 1 nanocrystal in the media. But what we can do is also, this is done also for the purpose of our picture also in terms of interactions that are more also intuitive, and also because if we do calculation, we have to do this decomposition. We can decompose this free energy of binding with different contributions that are the interaction of the free energy of the interaction of the nanocrystal to of the ligand to the nanocrystal, and this includes also we have to include also the ligand to ligand interaction, and then also a solvation energy term, because the solvation of this nanocrystal with all the ligands at the surface is not exactly the same as the sum of the solvation energy of the nanocrystal without ligands and the ligands solvated by the media, the environment. So this is not zero, the solvation term, because we have a great example of this, that it's micelles, that we know that when they aggregate, the aggregated system as a it's more soluble than the single component. And then we have to consider also that this term are directly related to the surface coverage. So as we show later, so different surface coverage will provide different free energy contributions. But let's see term by term what does it mean. So ligand binding energy. So imagine that you have a ligand to this binding to the surface, and this ligand will, this term will be favorable because it's always an electrostatic interaction between something that is negative with something more positive that is on the surface. And this is interaction that is mostly electrostatic, so it's favorable. So the free energy will be negative because it's favorable. And if you have, and this is, we can actually see how the free energy would change as a function of the surface coverage. Remember that in principle, we would always like to achieve, to attain 100% surface coverage, because that's when all the sites at the surface are passivated and you probably prevent the formation of trap states. So we said that it's always negative, and then it will increase more or less linearly when you add ligand, but then at some point, this maybe you saturate this free energy at high surface coverage, you can saturate this additivity of the term by adding one ligand at a time on the surface of the nanocrystal. So we can imagine that it has a linear component and then it reaches a plateau. This is like intuitive way of addressing the binding. So these lines are intuitive, so they're not computed because we still have to do the calculation on this system. So we expect that they behave like this. So this is the nanocrystal to ligand interaction. Then we can have the ligand to ligand interaction that we can expect that at low surface coverage, it's favorable. It gives a negative energy contribution, so a free energy, favorable free energy, because we can imagine that the ligands through van der Waals interaction tend to stabilize the system. But then at high surface coverage, it could be that you increase the bulkiness of the ligand and they become too much packed, and then they want to, they don't want to interact with each other favorably. So we can actually see that the trend, it could follow a line like this in the surface coverage. It becomes stabilizing at some point and then becomes destabilizing at high surface coverage. But it depends a lot, this term, on the bulkiness of the ligand. And then we have a ligand entropic term, so that we can also decompose it in terms of entropy and entropic term. The entropic term, it can be also important because the ligand that is alone has many degrees of freedom. When you put it on the surface, it loses some degrees of freedom, and this happens always. So we can expect that you immediately have a term that is unfavorable to move it on the surface, so it's always positive. When you increase surface coverage, you keep increasing, you keep blocking the ligands, the degrees of freedom of ligands to move, so it becomes always a positive term. And then we have this the free energy term due to the solvation energy. We said that maybe at the beginning, we don't know exactly how it behaves this. We expect that high surface coverage, you increase the solubility of the nanocrystal. So because similar to mine cells, so we expect this. Maybe at the beginning, this may be positive, maybe doesn't do anything. So maybe it's the same as a separate component. We don't know that yet. But then what we can do is that we can actually give all the free energy contribution in one single plot. And then what we actually have, that they become additive. So this is the total free energy of binding. And what we actually have is that if you put them all together and you add them up, so what you actually see is that you can have a maximum coverage, a maximum free energy at a surface coverage that it's not 100%, but it's below 100%. And maybe at this surface coverage, this is also the experience that we usually have in the labs, is that probably your nanocrystal after synthesis and washing, it's not completely fully passivated by ligand. And this is maybe a reason of that, because you have some contribution that go in opposite direction. So how can you improve this? You immediately notice that you want to reduce the entropic term, that it can be quite high, and also the ligand-ligand interaction. So you want to do the ligands less bulky, and you want to prevent the ligands, you want to reduce the degrees of ligand of freedom by designing the ligand in this way. So in this way, you can reduce these terms and actually put them down, and actually then having a high solubility that it's about at 100%. So this is the way that you can actually build the ligand. And because I don't have much time, I will, how can you do that? So you can put like a phenyl group right behind the anchoring group. So this blocks some degrees of freedom of the ligand, and so that you can improve the entropic term, as I said before. But you can actually do also this system not very bulky, so like this system, so that you also prevent the bulkiness term to be too much, to becoming too to not let the steric interaction becoming too important at high surface coverages. And then if you put together with what Peng said, so I will skip this slide, Peng in general said, okay, you can branch the ligand in such a way that you prevent aggregation between nanocrystals. And if you put these two together, then in the design of optimal ligands, you can have these ligands that favors binding, so it favors the ligands to move on the surface, but at the same time you can branch somehow, you need to branch this ligand to prevent aggregation, because this ligand alone maybe also helps in aggregating, because maybe it does a pi-pi stacking between ligands coming from different nanocrystals together. So then what you actually do, you may be designing a ligand like this. This is just a design we actually never tried, in which you have this branching part, terminal part, that prevent aggregation between nanocrystal, and this part below that blocks the degrees of freedom on ligands at the surface in such a way that you also minimize the degrees of freedom near to the anchoring group. So this in principle should also help to shift the binding equilibrium towards the nanocrystalline solution. And in this way, you can also avoid the spherical hindrance because the part that is near the surface is not very bulky. And in this way, you can actually design ligands, technically ligands, to fit better the nanocrystal surface. This is the last slide. I want to thank mostly Juliette in this work and Francesco that now is doing the screening of the ligands, and the other people that are in my group, and also the group of nanochemists that is led by Liberato Manna, because they do lots of synthesis, as you know, and we can actually interface with them very well. And I thank you for the attention.